Hi, welcome to the sixth lecture of EEE 107. In this lecture, we will be talking about linear continuous wave modulation. In this lecture, I will talk about how we modulate signals, how do we represent them in a way such that they can be transmitted over a physical channel. So recall the communication process where we start with an information source, where information is really just an abstract concept. So an abstract concept that cannot be realized or that cannot be transmitted in the real world. It's the job of a transmitter to represent that information and convert it to something physical, be it a sound wave, a light wave, or maybe even electromagnetic wave, even maybe image is, the definition of signals, right? So the transmitter will convert this abstract concept into a physical signal, which will be transported through a channel, right? So the channel, as I've mentioned in the previous lecture, introduces distortion, noise, and interference. And it's the job of the receiver to actually listen in the channel and correct any distortion that the channel makes. Okay? So let's recall what is modulation. As I've mentioned earlier, it's the process of adapting a given signal or information to a given channel. So depending on the channel, your transmitter will be different. Okay? But a common function of a modulator, right? The device that basically does the modulation process, most often than not, it involves translating your quote, not quote, translating the baseband message signal to a bandpass signal, right, of a much higher frequency, right? So what is the purpose of doing that? Why do we need to translate a signal into a higher frequency? A lot of the signals that we listen to, a lot of the signals that we can easily process using our conventional machines are actually in the baseband. What is the baseband? So if you look at the frequency spectrum, the baseband covers this f is equal to 0. It covers the DC frequency up to a certain bandwidth B. Right? So up to a certain bandwidth B, that is your baseband signal. It will be defined by how strong is the processing power of your equipment. And can also be defined by the channel and so on and so forth. And that's a different story. But in a sense, any baseband signal contains f is equal to 0. Right? That's why it's in the base of the frequency band. A bandpass signal does not contain this f is equal to 0. So an example of a bandpass signal is something like this. And it's a real signal, so it should have a reflection on the other side. So a bandpass signal has twice the bandwidth of a baseband signal. It occupies twice the bandwidth. But the advantage of converting this baseband signal to a bandpass signal to a higher frequency is that we can uh, make communication system. We can how do I coin this term? How do I We can use the frequency spectrum more efficiently. There you go. So by translating to different frequency bands, maybe this is your first signal, another signal can be squeezed in right here. And they won't interfere with each other because uh, you're using the spectrum efficiently. Right? Another reason why we want to convert our signals into higher frequencies is because of the antenna size. Right? Effective antennas, the length of the antenna, rather, so the length or the size of the antenna is indirectly proportional to frequency. So the higher the frequency, the smaller the antenna. So just a rule of thumb, the antenna size for wireless communications, if you use a speech signal which is around 200 to sorry 400 to 4 kilohertz, 400 hertz to 4 kilohertz, the wavelength of the antenna is around 100 kilometers. Sorry, the wavelength of the signal rather. And to design an antenna that will receive such a signal, you need one fourth of this, which is around 25 kilometers. So an antenna that size is not reasonable. Okay? So if we translate the speech signal to a higher frequency, then we can have a reasonable size for our antennas. So basically, we just want to miniaturize the antenna that we'll use so that we can translate even wirelessly. And it also applies to systems uh, that are wired also. So consider the telephone line. Okay, so I don't know how to draw a telephone line. Maybe something like this. So a telephone line, you have wires connecting uh, two poles, let's say. Okay. So in the telephone lines, we pass through, if you're familiar with a DSL, digital subscriber line, it uses the same telephone wires for communication, but it passes through communication signals. One is the telephone signal, the one that uses speech so you can talk to other people in a long distance, and the other is your internet service, the internet service of your digital subscriber line. If you look at the frequency spectrum of the signal in these two lines, so if you tap these two lines, you get some signal x of t. Okay, so if you measure the voltage, you store it in an oscilloscope, so on, and try to process its fast Fourier transform, assuming your oscilloscope is fast enough, it has a large sampling rate. Okay, the plot of the oscilloscope will look like this. The magnitude spectrum at here up to around 4 kilohertz. This is your speech signal, which is for your landline, for your telephone. And somewhere at the higher frequency, I forgot the frequency, I think it's around 100 megahertz or so. This is the bandwidth for your digital subscriber line. And this is where this is the bandwidth at which you transmit your internet data using the telephone lines. Okay? So that's another purpose of using modulation. So even if we're using the same line, we can transmit different data. We can transmit speech and uh, internet at the same time, internet data. Okay, there you go. So aside from reasonable antenna length, and also we can assign spectrum for different applications. And this is how the government regulates our frequency spectrum. Different parts of the spectrum use different applications. There's a different spectrum assignment for TV. There's a different spectrum assignment for Wi-Fi. There's a different spectrum assignment for, well, for the upcoming 5G, you have the higher frequencies. There's a different spectrum assignment also for radio and AM wave. Okay. So the basics of modulation is shown in the block diagram here. The modulator, you have two inputs for the modulator, the message signal and the carrier signal. And the modulated signal basically will be a function of time and of the message signal. So your carrier will have certain parameters in its your carrier's parameters rather will change depending on the message signal. Okay? So the modulation for in the communication sense involves a message in a carrier. The carrier, by the name, carries the message signal to be transmitted over some channel. Okay? So the carrier signal is the physical signal that carries the message signal through the channel. Okay? So there are two types of carrier signals. We have the sine wave and the rectangular pulse train. The sine wave is a carrier signal used for continuous wave modulation, and the rectangular pulse train is used for pulse modulation. Okay. So this is the two types of continuous wave modulation, the linear and the angle. So the angle, we will discuss this at the later lecture. For now, let's focus on the linear continuous wave modulation. So the linear continuous wave modulation varies the instantaneous amplitude of the carrier. As you can see here, the amplitude of the carrier at the output of the linear CW modulator varies with respect to the signal. If this is your signal, then see how the amplitude of the carrier is changing depending on the signal level. Right? So this is an example of your linear continuous wave modulation, as opposed to the angle continuous wave, where you vary the instantaneous angle. So that would mean if this is a sine carrier, so you vary the instantaneous phase of your carrier. Okay. So a type of continuous wave modulation is the amplitude modulation, or AM. And this is what is used for, well, AM radios. So the message signal is multiplied to some factor mu. This is the sensitivity or the modulation index. And you add 1 such that the DC level of your message signal is boosted, and you multiply that to your carrier wave. Okay. And we assume here that the maximum value of your message signal is 1 and its minimum value is -1. Right? So basically, your carrier message is bounded, your message signal rather is bounded between +1 and -1. So the constant is added to the scaled message signal before frequency translation, so such that the message signal will be above the t-axis. Right? So this +1 right here translates the signal above the t-axis, and this is essential when we're talking about amplitude modulation. And this will be apparent why it is essential in the succeeding slides. Okay. So if we compute for the output here, y of t, or s of t, sorry, it's better if we use s of t. S of t will be equal to this expression right here. The amplitude of the carrier times, cosine, I forgot the cosine, 2 pi fct times 1 plus mu m of t. Okay. And this is your AM wave already. The envelope, which is AC multiplied to this factor, if you are able to extract that envelope, you will be able to recover the message. As you can see here, the message looks like this. Right? It seems like the message is riding your carrier wave. So basically, in a sense, the definition of carrier is shown here. The carrier carries the message all over so that you can pass it through the channel. Okay? So a note on the modulation index. If the modulation index is less than 1, the AM signal envelope does not go negative. You'll have a you will have some space. Sorry, let me use red. You'll have some space between your upper envelope and your lower envelope. If mu is exactly 1, your AM signal envelope will swing at the maximum from 0 to 2 AC, and you'll have no space between the carriers, or you'll have zeros in your time domain signal. Now, if mu is greater than 1 and we want to avoid this, the signal envelope can go negative and you have an overmodulated signal. As you can see, this is your message signal, but if you try to extract the envelope of an overmodulated AM wave, your extracted envelope will look like this. So if you compare the original message to the extracted message, you have some form of nonlinear distortion. Okay? And this nonlinear distortion here is not recoverable. So we can only avoid it by imposing these conditions. So mu should always be less than or equal to 1. Right? In practical systems, however, we can't really in practical systems we can't really use mu is equal to 1. So in practical systems you use a mu that is strictly less than 1. Okay. So a demonstration will be provided during the lecture, and we'll use MATLAB to demonstrate that. Okay. And you will see how an AM signal is created. Okay. So now, of course, when we're talking about trying to transmit a signal over a channel, we'll need to know how much power it uses on a certain bandwidth. Okay. So you can analyze this using the block diagram. Okay. So the first part of the block diagram, as you see here, shows the spectrum of the message. This is the magnitude m of f. And once you multiply it by some mu, it will be scaled down. And if you add 1, you have a DC component. Okay. And then when you multiply it to the carrier, AC cosine 2 pi fct, when you multiply it with a cosine carrier, you're using the modulation property of Fourier transform. This will be split into 2, as you can see here. And this is now the spectrum of an AM signal. Okay. So to solve for the average power, we just integrate the mean square of the signal. Okay. So we can actually try to analyze that using the property of your cosine, the half angle property. This cosine squared will become 1 plus cosine 4 pi fct over 2. Okay. And if we're trying to get the average power, any cosine term will become 0. So this 1/2 will be translated here. So you have this. And the term here will become this term right here. Okay. So if you take the average of that, okay, so additional assumptions on the message signal. The message signal has 0 mean. There's no DC component. And the average power of the message is P sub m. So knowing that, this will become 0. And this will become P sub m. Therefore, the average power of your AM signal is equal to this. Okay? So we can actually rewrite this power of the AM signal as this. There's a component of the power from the AM signal that is from the carrier. And there's a component of power that comes from so-called message or the sidebands of the message. Right. So the power of the carrier is the first term right here. And the power of a sideband is 1/2 of this times this. So we can actually try to visualize that. So the power is equal to this. This is the spectrum of AM. The DC component earlier that was added and translated to a higher frequency, that is the carrier signal. And half of your message signal right here, outlined in red, that is your upper sideband. Oops. And the lower half, outlined in green, that is your lower sideband. And these are the components of power of a full AM signal. So this is also called a full AM signal. or a full AM wave because it's complete. You're complete with the lower sideband, the upper sideband, and the carrier. And as we go along with linear continuous wave modulation, there are different types of CW modulation that suppresses different parts of your full AM signal, and they're called something different. Okay. So anyway, this is the average power of an AM signal. So let's have an example. Consider the message here. So just a note that it satisfies this condition, and your carrier signal right here. How much should the gain Km will be applied to MFT to achieve 75% modulation? And then determine the power of the AM wave across a 100 ohm resistor. So note that we're feeding it to a 100 ohm resistor at 75% modulation. So how much gain should be applied to M of t to achieve 75% modulation? So that is when mu is equal to 0.75. Okay. So if you multiply mu times M of t, so mu should be 0.75 times your M of t, sorry, your mu times M of t here is equal to, you have a gain times your carrier. Yeah, okay. A gain times the message, rather. Right here. And then this Km times 0.25 should be equal to 0.75. Okay? So that would mean that Km is equal to 3. You need to feed your message into an amplifier with a gain of 3 so that you achieve a modulation index, or modulation index of 0.75 or 75% modulation. Okay, next. So when you compute for the power, when we're using this formula that I've shown earlier, the average of the mean square of a signal, you're referring this to a 1 ohm resistor. Okay? So this is the power across a 1 ohm resistor. So we already solved for mu, we already have a mu, we already have an AC. The power of the message needs to be computed first. Okay? So P sub m is the power of, just note, of the normalized message. So earlier, our assumption in the lecture is the magnitude of m of t should be less than or equal to 1. If P sub m is, if the message signal is normalized and it's a sinusoidal wave right here, if it's normalized, then we're trying to get the power of only the cosine component. The power of a sinusoid is 0.5 watts. And mu here is 0.75. So just plug that in. That's 50 squared over 2 times 1 plus 0.75 squared times 0.5. Okay? And that is equal to 1.6 kilowatts when normalized to 1 ohm. Okay? If we want to use 100 ohms as a reference, then we have to divide this power by 100 ohms, and the power of your signal, if you feed it into a 100 ohm load, is equal to 16 watts. And that's the answer. Okay. And finally, to detect our signal, we use what we call the envelope detector. So I'll show it to you using Simulink. But how does it work? The diode rectifies the negative part of your AM wave. So if this is your AM wave, okay, after a half-wave rectifier, right here, the AM wave will be split into two. The negative parts will be deleted because of the rectifier. Okay? And we're only left with the positive part of the AM signal. And if you pass that through a low pass filter, since the low pass filter is very slow compared to the fluctuations of your carrier signal, passing that through an LPF, oops, you will only get the envelope of the signal with some distortion right here. Right? Since we have a diode in the half-wave rectifier, any backflow of current will be blocked by the diode, and your low-pass filter your capacitor will only discharge over these two resistors, making it very slow. So if it's very slow, then it won't be able to keep up with the fluctuations and will only be able to extract the envelope of your AM signal. That's why the envelope is very important, especially when we're trying to receive a full AM wave. Right? So this is uh, an example of a message of a receiver of AM wave. So uh, it just reverses the process of full AM modulation, and it's actually quite simple to implement the circuit. So that's the one of the biggest advantages of a full AM wave is that the receiver is very simple to implement and it's very cheap. Okay? And that's the end of this part of the lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.